Okay. So let us. So last time we covered why we take Z transform, and I mentioned that primary reason for taking Z transform is to check the stability of a system. And it's easy check, and the check is that you check if the region of convergence contains the unit circle or not. If it contains, system is stable. Okay, and then we covered that for a causal LTI system, all the poles must be inside the unit circle. For anti-causal LTI system, all the poles must be outside the unit circle. So now here we will learn how to take inverse Z transform. Z transform can be taken as a simple summation formula, so you can use that to actually compute Z transform. But for inverse Z transform, if you want to, though there is an inverse, so integral or inverse relationship which can help you to actually compute the inverse Z transform, which is the counter integral. Some of you might have seen it in your math course, but usually this is not used to compute inverse Z transform. You try by inspection, you recognize the common transform pair, so you have the pair sheet, you compare, you find out the pair, and then use that pair to compute inverse Z transform. Okay, so this is primarily this method is used, which is by inspection method and partial fraction expansion method. Now, these are the two effective methods for computing Z transform, though you can do power series expansion as well. So primarily the 2 and 3 are used for computing inverse Z transform. This is the Cauchy integral definition of computing inverse Z transform. So not worry about this, but on the unit circle, if this counter is on the unit circle, then it is the Fourier transform, which runs from -pi to pi, and this is the formula which is derived, which can be derived if you want to, from this integral, and we will not use it. Primarily we use the partial fraction expansion and the inspection method. So you will be given, our interest really in Z transform is in these type of expressions where you have something in the numerator and in the denominator, and this is what our core interest is in finding, because we will shortly find out something in the denominator means it's an IIR system because it has poles. A denominator means an IIR system, and numerator means only an FIR system. So an FIR system and an IR system, and remember from our previous chapter that BKs are the coefficient of X and AKs are the coefficients of Y. So these are the same coefficients in a difference equation, coefficient of Y, coefficient of X. So usually a polynomial is given to you, that this is a polynomial which has a numerator and a denominator. You convert this polynomial into factors. So there is a MATLAB function can also help you to actually compute the factors. So you compute the factors, and after you compute the factors, you will find all the roots of the numerator are called zeros, and all the roots of the denominator are called poles. So DKs are the poles and CKs are the zeros of the system, so to say. And we know the partial fraction expansion method, that you first do a long division. If the power of the numerator is greater than or equal to the power of the denominator, so you do long division to make it smaller, and then you compute partial fraction. So this is what is shown here, that if the power, if m is, which is the power in the numerator, is greater than or equal to n, you do long division, and that division will generate these factors, and I'll show you an example. And then you have all the partial fractions of the expressions. AK are the constants which you compute, and 1 minus dk z minus k, z minus 1 is in the denominator. So, and then now it's very simple. If you complete this step, now it's very simple to compute. We know that the delta n minus m. So you have the inverse pair will be used to compute the transform delta n minus m. The z transform is z minus m, and all z except 0, because it is 1 over z raised to the power m. If z is 0, it is 1 over 0. So the region of convergence is the entire z plane except z is equal to 0, right? And obviously if it is m is negative, then it says infinity, but these are not important. Our interest is really in unit circle. So we can safely say the entire z plane is the region of convergence, and delta n minus m. So you go in reverse direction. If you have any factor in your expression, its inverse z transform is very simple to compute. For example, if I ask you what is the z transform of this 0, 1 and 2, let's say it is 3, it is 2 and it is 4. So z transform of this, I know this is an impulse at 0, this is an impulse at 1, this is an impulse at 2. So impulse at 0, z transform is 3, because z transform of delta of n is 1. Okay, so delta of n, this is delta of n multiplied by 3, means 3 delta of n is 3. A z transform of delta n minus 1 is z minus 1. So you have plus 2 z inverse. And this is plus 4 z minus 2. So if you are given this, you can compute this, right? So given this, so this is how you go in reverse direction. And then for every factor you have 1 over 1 minus a z inverse. Its z transform is either this or this, a n u of n, or minus a n u of minus n minus 1, given that whether it's a causal or an anti-causal system, a right hand side or a left hand side sequence. So knowing these pairs will help you to compute the z transform. We know how to compute partial fraction, so you can you need to go back, learn that how to compute partial fractions. So the partial fractions are computed. First you write them in, you factorize the denominator, okay, and then you divide, you multiply the whole expression by the factor which you intend to compute, and that cancels out, and you find the coefficient by putting this equal to 0, as it says. You put z is equal to dm, you find one value, then you keep doing that. So that is how the partial fractions are computed. This is how it shows that you are dividing by this and putting z is equal to dm. That will help you to compute the partial fraction, and you'll see that there is an example, and I'll quickly show you that. So all these z's, power of z's, will give you delta of n's. Okay, the power will be the delta n minus 1, delta n minus 2. So all these factors will give you impulses, and all these factors will give you exponentials. So there will be only two parts. One is you have these will give you impulses, and these will give you the exponentials. And because dk raised to the power n, u of n if it is right hand side, and if you are assuming it left hand side, so you will give you this exponential. So let me, okay, so here is a good example which we already did. For example, you are asked to compute the inverse z transform of this a over 1 minus this is being partial fraction. So you are given a over this plus b over this plus c over this. Okay, so there is a pole at a, pole at b, pole at c. So pole at a, pole at b, pole at c. So there are three poles. If you assume that all a, b and c's are less than 1, for example, okay, and this is a right hand side sequence, you can very easily compute inverse z transform. Region of convergence will be outside the outermost pole, and this will be a, which is constant, a of n u of n, plus b, which is a constant, b of n u of n, plus c, a constant, c of n u of n. And then this is where you assume all of them are left hand side sequence. inside the innermost pole, and all will come with minus n minus 1, minus n minus 1, minus n minus 1. And this is where you assume this right hand side and the other two are left hand side, you get this, or this is where you assume these two are right hand side and this is left hand side. So you get 1, 2, 3, 4 expressions. So the important is every denominator, a factor in the denominator, every root means an exponential in the impulse response. Every root means an exponential in the impulse response. So roots of the denominator are very important because these are the poles of the system. So this we have covered. Now this is a good example. So look at this. This is an example. You are asked to compute inverse Z transform of this expression. Okay. So you make factors of this, factor of this to find poles and zeros of the system. Okay. You factorize it, and MATLAB can help you to factorize. Otherwise, you must have learned that how to factorize an expression. So factorize this. So these are the factors. Okay. So where is the 0? At minus, and how many of them are there? 3. So there's 3 zeros. Then where is your poles? At 1 and at 2. So these are the poles and zeros of the system. You can plot poles and zeros. Then the next job is that you do partial fraction. Now the power in the numerator is greater than power in the denominator. So you do long division. So you perform a long division. And this is the long division. So you put this in this order. So Z minus 3, 3 plus this, and this denominator you divide first with this. So this cancels out. You get this. Then with this cancels out. And now the remainder has a power which is less than the power in the denominator. You stop here. So you should keep dividing until you hit where the remainder has a power which is less than the power of the denominator. So we know that. So you stop here and you rewrite it. You say, okay, this is what I get. So these are the two, a constant and this, minus the remainder which is this, and the denominator which is this. Okay. So now you need to make partial fraction of this expression. Okay. So this, need not to worry about this. So these are the constant. I know its inverse Z transform is what? 2.25 delta of n. It is 0.5 delta of n minus 1. And this will be a constant. In exam, I don't mind even if you just write a constant A1, A2 instead of actually going and computing the partial fraction. So you can just assume anything. But the important is you need to know that this will be one partial fraction, this will be another factor. So there will be a constant, and constant you can compute if you want to, but so this is how you compute the constant. But if you don't want to do that, you can live. But this is the constant minus 8 and this is constant 6.75, and now you can actually compute the inverse Z transform of this expression. And again you can assume several things. Can this be a stable system? Any choice of expressions. It is a pole at where? 1 and a pole at 2. Can you think of a scenario where you assume something right hand side, left hand side? Can it be a stable system? Never, because it has a pole on the unit circle. So unit circle will never be in the region of convergence no matter what you do. So because we know that a region of convergence cannot contain a pole. Either it will be outside 1, inside 1, or outside 2. So these are the two choices, or between 1 and 2, but not 1. So 1 will always be excluded. So if you place a pole on the unit circle, it's interesting. So we'll try to give them a MATLAB exercise where you actually place a pole here and find its impulse response. So any guess? If you place a pole here on a system and you find its impulse response, it will be a sinusoid. It will oscillate. So especially if you put 2 of these here. So we'll do a MATLAB exercise. If you just put 1, it will be an exponential, a cosine and a sine. And this is how you generate, this is called oscillator. So if you want to generate an oscillator, put a pole at a particular frequency. If you want to generate this particular frequency oscillator, put a pole here and find and give an impulse, it'll start generating a sine and a cosine for you. So do the exercise and find out why it is so. But the inverse Z transform, these are these several options. One is 3 options we know. One is both Z is greater than 2 outside the outermost pole. The other one is inside the innermost pole, and the other is in between 2. So these are the options for this particular system. So this we know that is not a stable system. Okay, then this is the MATLAB function which can be used to find the partial fraction residues R, P and K. You give the coefficients of the numerator, you give the coefficient of the denominator, call this function. It'll give you R and P. R, P are the poles, R are the corresponding coefficient. For this pole, this is the coefficient. For this pole, this is the coefficient. These are the constant polynomial. So this 0.2.25, 0.5 Z inverse. Here pole is -2 and coefficient is 6.75. Pole is -1, coefficient is -8. So this is a function which can help you to compute the partial fraction expression for any function. And we have already covered this, and this will be using the delay we have covered, or shift property, convolution we have covered. A convolution is interesting, that convolution in time is multiplication in Z domain. Why? Because we also call convolution is primarily multiplication of polynomials. Why? Because let's say if I ask you to perform convolution of this function with this function. So let's say this is 2, this is 4, this is 3, this is 2, 2 and 3, for example. If I ask you to perform convolution, so you need to do flip, drag, do all of that. The other way is find Z transform of this and Z transform of this. What is Z transform of this?
2 plus 4, 4Z.
This is the case, and this is 2 plus
3Z.
So simply multiply them together. It's a polynomial multiplication. You can assume Z inverse is equal to X if you want to. So this will become 2 plus 4X plus 3X square, 2 plus 2X plus 3X square. So multiply them together and that will give you convolution. 2 2's the 4, 2 4's the 8, X plus 6, X square, then plus 2 2's the 4X plus 8X square plus 6X cube plus 6X square plus 12X cube plus, and this is really the flip and drag what you do otherwise. So it is 4 plus 8 plus 12, this is in fact Z inverse plus whatever, okay, 20Z minus 2 plus 18Z minus 3 plus 9Z minus 4. So you can actually plot that you get 4, you get 12, you get 20, you get 18, you get 9. This is what you get. So this is another way of performing convolution, that you simply multiply the two polynomials together, you get the answer of the convolution. In fact, whenever you are multiplying two polynomials together, you can use MATLAB function convolution to do that. If you have two polynomials, you want to multiply them together, just use convolve, write the coefficient of 1, coefficient of 2, it will multiply the two polynomials together. Convolution is in fact multiplication of polynomials, right? Because of this property of Z transform, which says you take Z transform of 1, the take Z transform of 2, what you get is the polynomial, and then multiply them together, means it is you're convolving in the time domain. So now comes the actual topic of importance for us, and that is an IIR system, an infinite impulse response system. We know an infinite impulse response system is represented by a difference equation, and this is perhaps a good example because we know this is a difference equation with A and U of n as its impulse response. Now if you take Z transform of both sides, Y of n is Y of Z, A is a constant and a delay means Z minus 1. Y of Z plus X of n is X of Z. So you bring A on this side, this is what you get, and then take the YZ common. You get 1 minus A Z inverse is equal to X of Z. So Y of Z over X of Z is equal to 1 over 1 minus A, and I'm doing this just to make sure that it's not small y small x here, small capital Y and capital Z. This usually is called YZ over X of Z. I know because X of n convolution H of n is what? Y of n. If you take Z transform, we know Y of Z is equal to, and convolution is multiplication in Z domain. I know this, right? If the convolution, if you take Z transform both sides, convolution will change into simple Z transform. So H of Z is in fact Y of Z over X of Z. So this is the H of Z. So what you see here is in fact H of Z. H of Z. Okay. So look at this. These are really the, you need not to go through all of this. H of Z is the, if you put all y's on one side and x on this side, so the denominator is the coefficients of y. Y of n will come with constant, n minus 1 will come with Z inverse, n minus 2 will come with Z minus 2, Z minus 3, so it is 1 and this is minus A, and coefficients of x will appear here. For example, if I ask you what is the H of Z for this, X of n minus 0.9, Y of n minus 1 plus 0.8, Y of n minus 2 plus 0.6, X of n plus 0.8, X n minus 1. Though you can go through this and find H of Z, or you can directly write H of Z is equal to 0.6 plus 0.8 Z inverse 1 minus 0.9 Z inverse plus 0.8. So this is how you write. So you can, looking at the difference equation, you can write H of Z. Okay, so this is the first thing you do. Knowing a difference equation, you write this. Still I cannot comment on the stability. Why not? जी नहीं, H of Z जो है वो Y over X है, लेकिन Y appears here and then it goes in the denominator as I did here. ठीक है ना? So the coefficient of Y's will appear in the denominator and the coefficients of X will appear in the numerator. So this is important. Coefficients of Y will appear in the denominator. ठीक है? अब if I ask you to compute its inverse, find poles and zeros. First thing, that is what you need to do. If it is a causal LTI system, when will it be stable? If all the poles are inside them. This is a simple trick, and that's why you learned all this Z transform, to know that you write, you look at the difference equation. Okay, look at the difference equation, write this expression and find all the poles and make sure all the poles are inside the unit circle. And this is an interesting exercise. Once you have a 10th degree polynomial, let's say you are designing a dynamic system and that dynamic system has 10th order difference equation. So you need to compute how many? 10. So you need to compute 10 order this and 10 poles, and you need to make sure all poles are inside the unit circle. So you compute 10 poles, and this you have to do every time you design. You find the poles and you say yes, they are in the unit circle, so this is a stable system. this is the exercise which we do, and this can help you to actually compute h of n. We know how to compute h of n, right? So you make factors, then there will be, how many exponentials will be there in this? How many exponentials will be there? There will be 2 exponentials, because there will be 2 factors. Z minus 2a, there will be 2 factors, 2 exponentials. There will be 2 poles. Okay? There will be 2 poles. Depending upon if you compute b square minus 4ac from your old math, is minus b plus minus b square minus 4ac divided by 2a. So this is how you compute. Now another interesting perspective of the poles. What if b square minus 4ac square root is plus minus j? Here it is j. Minus b plus minus b square minus 4ac, sorry, j खुद ही आ जाएगा यहाँ से. What if b square minus 4ac is negative? What will happen? You will have complex poles. If b square minus 4ac is imaginary, b square minus 4ac is negative, you get imaginary poles. But they will always be conjugate of each other. This is important. You may, looking at this expression, depending upon, remember this is a, this is b, this is c. Okay, so c, b square minus 4ac, compute this. If this is positive, good. If this positive means what? There will be square root will be positive. What is square root will be positive then? So you get real poles. What is meant by real poles? Real pole means that poles will be here on this line. They may be anywhere on this line. Okay, these are real poles. We'll see the significance of these poles. But that is the whole story. Now, you design a system, you plot the poles. And you also plot the zeros. You plot the poles, you plot the zeros. So plot the poles, if they are real, they are on this axis. If they are not real, and if the coefficients are real, if the coefficients are real, mean the coefficient of the difference equation are real, at least it guarantees you one thing. If the coefficient of the difference equation are real, it guarantees you one thing, that poles will be either real or conjugate of each other. Okay, the poles will be real, or if they are not real, they may appear here, but if a pole appear here, a pole will also appear here. Guaranteed. For real coefficient difference equation, will be poles appearing as conjugate of each other. So coming back to, we'll spend a lot of time learning about all these poles and zeros, but here to go G.
जो भी आप बात कर रहे हैं कि वो जब आपके पास coefficients वो real होंगे तो आपके पास conjugate pairs में आएंगे.
Always.
So इसकी significance क्या है?
Significance है. I'll tell you what is the significance. I'll tell you let's not, we'll be jumping a lot, okay? I'll tell you that, but remember that they will be conjugate of each other, okay? Or it's otherwise as well, that if poles are, one significance, if the coefficients are real, poles will always be in complex conjugate pair, okay? If you are trying to find out poles of a system, if you find a pole here, in a complex, you need not to find another pole. Okay? You know the other pole will always be here. Okay? So people use these tricks that if there is one pole in complex plane, it means guaranteed. It means the coefficient of the difference equation will be complex. If the poles are not conjugate of each other, there is one pole in the plane without any conjugate pair, it is guaranteed that the difference equation, once you make a difference equation out of it, and we'll do this exercise, and now this is what you need to learn: a difference equation, pole zero diagram, impulse response. So you need to learn all these three things. Okay, so the three things are, you need to learn about the difference equation, you need to know how to compute h of z, means drawing all the poles, and we are least interested in actually finding the impulse response in practice, but at least from academic perspective you need to know that. We are not really interested in actually computing the impulse response. All I need to know is, this is the difference equation, this is my pole zero diagram. And that by looking at the pole zero diagram, I can comment whether the system is stable or not. Okay, I can do a lot of analysis. I will know a lot about the system, but difference equation will not tell me all those things. Right?
So you if we have a conjugate pole, and it will be in the form of cos omega plus j sin omega. So will it be a discrete time or a continuous time?
No, it is this is the Z transform, which is a transform. System is a discrete time system. Z transform is used only for discrete time sequences. Okay? Z transform, you can only take Z transform of a sequence. Remember, the reality is time. This is only for analysis. So you go back, you implement difference equation. Z transform you never compute. Z transform otherwise is a continuous. Z is a continuous variable. You don't compute Z transform. I'm not asking you to compute. Don't put values and start computing Z transform. All we do this to find poles and zeros. So this is the rationale of using Z transform, that you find poles and zeros, find whether all the poles are inside the unit circle or not. Okay, this is the rationale of going through all this. And so keep saying this in signal processing, that pole zero diagrams are important. That what is your pole and zero diagram. So here is the difference equation can give you h of z, and h of z can help you to compute the h of n, which is for the causal system is a n u of n. Okay, so you can compute from the difference equation you can compute h of z. There is only one pole at a, and then you can compute, so you can compute all of this given our difference equation. So see, MATLAB is very good in actually plotting the pole zero diagram for the difference equations you design. So here is that. And now if region of convergence, if causal z is greater than a, so we know this is what I just did, that you do this, you get h of z, you get h of n. And if you are asked to compute the Fourier transform, okay, simple. Just replace z by exponential minus j omega. Z inverse by exponential minus j omega, z by exponential j omega. So wherever you see z, if region of convergence contains unit circle, only then you can do this. Remember that from z transform it is very easy to compute Fourier transform. All you need to do is just replace z by exponential j omega, r is equal to 1. So this will give you, and we have seen this expression, h exponential j omega is equal to 1 over 1 minus a exponential minus j omega, and this is the h of n. This is an IER system, and these are the different perspective of a system. A difference equation 1, a system function h of z 2, which means knowing all your poles and zeros, frequency response 3, means that actually plotting the frequency response, impulse response is 4. So whenever you design a system, analyze a system, okay, these are the 4 things which you want to see. This is to actually implement a system. Implementation. This is actually to analyze. Okay? You analyze a system, you see whether it is stable or not, see location of poles and zeros. This is to find its frequency response. What this system is going to do to my signal. We have already learned about this. This is how the system will shape my frequency spectrum. And this has no practical significance, just the impulse response of a system, seeing it is an infinite impulse response. If it is unstable, it will diverge, otherwise it will converge. But once we talk about system, okay, whether it is a dynamically varying or adaptive system, we always talk about difference equation and the system function and the frequency response and maybe the impulse response. Let me try to run MATLAB here. Okay. This is the MATLAB toolbox. As you go down, it says filter design toolbox. As you go, it says design and analysis tool, FDA tool in MATLAB. And this is what? Oh, no, don't do this. Okay. Well, I at this point want to show you is the analysis which MATLAB does for you. So at this point we'll not worry about what these things are. I only want to design something and show you the different things which MATLAB. So MATLAB basically design a system, and design means it gives you B's and A's, the coefficient B's and A's, and also tell you the order. 31 means it is using 31 previous values, y n minus 1, n minus 2, n minus 3, n minus till n minus 31. Okay. So if you actually want to go and read these values, B's and A's, you can do that. These are B's and A's. Okay. And it's showing you, I want to see it. So these are the coefficient of the numerator. Okay, this is B0, B1, B2, B3, B4. So if you keep going down, these are the coefficient of the numerator, and these are the coefficients of the denominator. Usually the first coefficient is 1 because this relates to y of n. So this is actually a difference equation which MATLAB has designed for you. Once you design a system in MATLAB using the toolbox, it will give you B's and A's. This is for implementation. In MATLAB you can actually export this to any target. You say, I want to export it to a Xilinx or a Code Composer Studio on a digital signal processor. So it'll make a header file, put everything there. Or you can export it to, for Xilinx you can export this file, what you have designed. But important is the analysis. The analysis requires you to plot poles and zeros. So here are poles and zeros. Okay, what do you see? The poles are shown with cross. They are going to be how many? 31th order system will have how many poles? 31. So they are going to be 31 poles. If you look at the poles, they are in complex conjugate pair. A pole here will guarantee a pole here, a pole here, a pole here, a pole here, a pole here. Okay, so they may be anywhere, but they got to be inside the unit circle. So these are zeros. At this point, let's not worry about zero, but the zeros are there, they are significant. But our worry is you can find several zeros outside the unit circle. They are not going to disturb the stability of a system, so you don't mind. But all the poles are inside the unit circle. So this is important for us to plot this. You say, okay, I have designed a system where all the poles are inside the unit circle. Okay, the poles are inside the unit circle. Then you say, okay, let me see the impulse response. So this will give you the impulse response. It is an infinite impulse response system having 31 exponentials in it. 31 exponentials. So if you put all the exponentials together, this is what you see. Otherwise, no significance as such. You will not make out anything, but just for completeness, you see, though you cannot really plot it to infinity, so they have plotted it will be decaying. Anything which is stable will have a decaying impulse response. So it's a decaying impulse response. Okay, then comes and we are very interested in the frequency response. This is the frequency response. Okay, we'll learn more thing about the dBs and how good it is, which is a very good filter. It's all 0 dBs mean all ones, and even it's minus 100 dB, so it's perhaps 0.0000 something. It's shown in dBs. It's a very good filter, and this is how you analyze. You can see the magnitude response, you can see the phase. Remember, it's an IAR. IR में what type of phase do you expect to have? Any guess? This is the phase response. It's non-linear. Okay. Now you can design an FIR filter. In FIR filter, what do you expect? Any poles? All zeros. In an FIR filter, there is no pole because there is no denominator. All zeros, and it says 50 poles at 0. That means it's Z minus 1, Z minus 2, Z minus 3. Order is 50, means 50 zeros in the system. It's an FIR system. You design, at this point we don't know how to design, just giving you the analysis tool. The analysis tool can help you to design system, and how you only need to mention the sampling frequency and where you want to stop frequency. So you mention all these things, and it'll design B's and A's for you, and you can export it. But the important point is that this is what we have learned, that once you are designing an IER system, the location of poles and zeros are important. Poles to check the stability, and zeros to shape the frequency response, and we'll see how. And these are important things which you need to learn. The difference equation, you need to see difference equation to implement, system function to analyze, frequency response to see how it is going to shape your frequencies, and then impulse response. So for example, this is the magnitude and phase response of a system with one pole inside the unit circle. This is the location of pole. These are the zeros. Usually we also plot zeros. Why? Because if you see this, so it is actually Z inverse is what? A over Z. So this is Z over Z minus A. So Z, what is 0? Z is equal to 0 is this at 0. So this is 1 0. 0 of the system is 1, which is at 0, and pole is at A. So there are poles and zeros, and Z is equal to 0 is 0 and a pole. So usually you will have zeros and poles, and this is how you plot the magnitude response and the phase response. Okay, so to generalize this, you will be given a difference equation. Y, coefficient of y is on this side, coefficient of x on this side. You take Z transform, but directly you can come and write it like this. All the coefficients of y's will appear in the denominator, all the coefficients of x will appear in the numerator. So you can directly write. Then you need to go through the drill of computing all the poles and zeros. What do? Find all the factors, find all the factors. They'll give you poles and zeros. Done? Okay, so plot poles and zeros, find if all the poles are inside the unit circle. Yes, you say system is stable. Go to the next step. If power m is greater than or equal to n, do the long division. Do the long division, make it less, then make all the factors, partial fractions, and then compute h of n if required. Okay? So this is the drill, that you make factors. These all are the zeros, these all are the poles, and you need to make sure the maximum pole region of convergence is outside the outermost pole, the magnitude, jiska magnitude is maximum. And for stability, make sure that this is inside the unit circle, and then make long division. This is the result of long division, and then you take the inverse Z transform to actually find the impulse response. This is the impulse response. So h of z and h of n, as for the causal system, that is h of n is 0 for n is less than 0. For causal system, this is what. And then you need to compute the frequency response, and that is just change z with exponential j omega. If you do this, it'll give you the frequency response, h exponential j omega. So this is the frequency response of a system. To summarize, this is what we have learned so far. A system is an LTI system, a linear time invariant system, can be characterized by an impulse response. For delta of n, you get h of n. So if you know this, you can find the output of a system due to any input x of n. Frequency response is if you input exponential j omega n, then the response you get at the output is the same exponential j omega n multiplied by a constant h exponential j omega for a particular frequency. So a complex exponential will change in its magnitude and phase after going through an LTI system. This we have learned. We have learned that convolution in time is multiplication in frequency domain. So the convolution here will like this, and same is true for z domain. And this is how you compute h of z, making for the difference equation. This is how you write, and this is if you remove z by exponential j omega, I'll give you the Fourier transform. Okay. Now these are a few examples which helps you to understand the stability, causality, that if this is the system half n u of n, okay, this is a decaying exponential. If you compute its z transform, it is 1 over 1 minus half z square. This is the pole at half. The pole is here, which is inside the unit circle, so it is a unit of its region of convergence contains the unit circle, so it is stable outside the outward hai iska, so causal and stable. Similarly, this is an anti-causal system and is an unstable system. How you figure this out? Because you know the pole is now the unit circle, it does not contain the unit circle, so it is an unstable system, an anti-causal and unstable system. And this is also a causal and unstable system. 2 of n u of n, should do this, it is pole at 0 at 2, so this is not a stable system, this is a stable, unstable and causal system. So causality and stability, these are two different things. And this is another an anti-causal and stable system, minus 2 raised to power n u of minus n minus 1, because the region of convergence contains the unit circle. So this is about the z transform and how it affects your analysis. So again, let me summarize this, that okay, from our perspective, the most important relationship is this. This is M if this is an FIR system, then n will be equal to 0. There will be only y of n, and usually a of 0 is kept 1. If it is not 1, then you divide everything by a of 0 to make it 1. So this is, if a system is an FIR system, then a0 is always 1 and rest all a's will be zeros. So it will never grow beyond y of n. So everything will be here on this side, which is b k x of n minus k. K goes from 0 to m, and so everything is here. Okay. This is important from implementation perspective. This is important from design perspective. So in design, you give specifications as I showed you in MATLAB. So MATLAB will come back and give you AKs and BKs. Okay? So you tell MATLAB will come back and will tell you these are your AKs and BKs if you are using MATLAB to do it. And you can only use MATLAB because it will be moving towards the second part of the course. You can ask MATLAB to do this. We'll see that they'll generate some exercises for you to just design systems and see how AKs and BKs look like. So AKs and BKs are fine. You find them. But then this is the analysis that MATLAB is doing for you. So it's very convenient because MATLAB is there and you are designing it offline. So MATLAB is there for your help. You design, you analyze, then you can port it on FPGA, you can port it on a DSP processor, you can port it in a C file, header file, actually implement the difference equation. So very convenient. Analysis will show you whether all the poles are inside the unit circle or not. Okay, so I have shown you, you plot it. If all the poles are inside the unit circle, you say system is stable, causal and stable. Right? If there is a pole on the, let's see if there is a pole here. What is the h of n? How do you compute h of n? If a pole is at, let's say, I call this exponential j omega naught. If there is a pole at exponential j omega naught, can you give me the h of z for this? 1 over 1 minus anybody? Exponential j omega. This is the h of z. So remember, though up till now we are always focusing either putting a or b or c here, this may not be the case. This may, you may find here exponential j omega naught. Okay, exponential, because the pole is at exponential j omega. You may find a complex number here, r exponential j omega naught. You may find a real number, which is very convenient because we are used to seeing 0.9. So it says 0.9, and what is h of n? 0.9 and u of n. What is the difference equation for this? Y of n for this. Y of n is e raised to the power j omega this is the equation. Okay, what is the impulse response? What is the impulse response? Of this, take inverse Z transform. Exponential j omega naught n u of n, because it is a of n u of n, so the n will appear here. This is the impulse response. What is an impulse response? That if you give an impulse, it will generate this. What is exponential j omega naught n u of n? G? Oscillation. So this is in fact exponential j omega naught n u of n is in fact cosine of omega naught n plus j sine of omega naught n. Okay? So this is your h of n. Means if you give this, and though it is it a stable system? No, it's not a stable system. Because why? Pole is at on the unit circle, so region of convergence does not contain the unit circle, so it's going to be outside the pole. So this is the reason it is. Okay, tell me, what if I only want to generate a cosine? What do you do? G? Conjugate. You take conjugate of this here. If you only want to generate cosine. So a pole here and a pole there will make sure that you don't see, remember you are here, you find what? You find a complex exponential, a complex number here. This is a complex number. Put omega naught, this will be a complex number. Let's say pi by 4. So exponential j pi by 4. This is a complex number. So if there is a pole, not a conjugate pair, if a pole, your difference equation will have a complex number. Okay? If there are two poles, they are conjugate of each other, you won't see that. Okay, you will only find, and we know the expression that was the h of z which was given to you. If there are two poles like this, it will be a second order polynomial in the denominator involving y of n minus 1, y of n minus 2, but no complex term in it. So coming back to this, okay, if in MATLAB I want you to generate sine and cosine, you design this particular filter. I ask you to generate sine and cosine with frequency pi over 17, for example. Design a system, a a first order IIR filter which can generate a cosine and sine of pi by 7. What do? You generate, so what is A here? A kya hai idhar? What is A? 1. Anybody, what is A in the difference equation? Remember, A's are the coefficient of y, B's are the coefficient of x. What is A here? And 1 and minus exponential j omega naught. This is the A vector. And what is B vector? B vector is 1. Okay. So how do you get this? By using the filter command. You write y is equal to filter b comma a comma x. What is there in x? What do you put? X is the input. So what should be the input? To generate cosine and sine, what should be the input? Any guess? An impulse. How do you write impulse in? 1 at 0, 0, 0, 0. As many as you want. So it will generate only these many output samples. So 1, and you can put zeros. There is a function in MATLAB. You say 1 zeros 500, let's say. So we'll put 1 and 500 zeros, and it will only generate 500 samples for cosine and sine. Okay? So this is how you generate a cosine and sine. This is an oscillator. Okay? These tricks are also used in analog circuits. Okay? If you want to design an oscillator, you need to place a pole on the y-axis and then just give an impulse. It'll start oscillating. The system will start oscillating. It'll go up, down, up, which is not good. If you think of a physical system, it is oscillating. This is not good. But an unstable system, if you only apply an impulse, the system will start oscillating. Okay, this is bad thing. But if it is stable, it will oscillate, and finally, slowly, it will decay down and also will slow down. If it is a physical system. Okay? But here, sometimes you want to generate the oscillations. This is what you do. If you have a circuit, you can use a circuit. But if it is signal processing, this is a thing which can be used to generate sine and cosine, and this particular function. And this, remember, is a complex number. Okay, this is a complex number which you can actually compute using your calculator. So put a complex number here. Use this function. It will generate sine and cosine for you. So this is important. Okay, I'll just spend some time in just starting the next chapter. I'll cover a part of the next chapter, but then we'll move to the second part of the course. Okay, though we may spend more time here, but we'll move to the second part of the course where we will be designing B's and A's dynamically, modeling system. So we'll spend a little time here learning about sampling, just a little about sampling so that you know what sampling is, and then we'll move and do the sampling is a process where you convert a continuous time signal to a discrete time signal. We know this because sampling will lead us to the advanced topic where we said we need to learn about the polyphase filters and band pass sampling and multi-rate signal processing. So this is why we need to learn this. So in sampling, you take a continuous signal and you sample it, discretize it, and then use a DSP to process this, and then you may need to convert this back to continuous. In your book, it uses a terminology continuous to discrete conversion, and then it says it is not analog to digital conversion. It says to learn sampling, let us not worry about the exact value which you get once you sample a signal. Okay, once you sample a signal, usually depending upon the resolution of the A to D converter, okay, you may or may not able to exactly represent this point. If let's say it's a 4-bit A to D converter, so how many levels do you have? 16 levels may not have this, not exactly this. So then you need to quantize it. You need to either take it to the upper level or the lower level, right? We know, we all know about this. So the book says let's not at this point worry about the quantization. Let's just say there is a way for you to represent a sample exactly, right? And once you bring the quantization, it'll only add some noise in the process. So that's why the book uses continuous to discrete or discrete to continuous systems. And to understand the process of sampling, let me first simply explain, though it's not really difficult to comprehend. Sampling, we know that a signal has several frequencies. Okay, and in fact, if you want, you can break a signal into so many complex exponentials. We have seen that a complex exponential is sine and cosine. So once you look at a signal in frequency domain, you will find a spectrum. Okay, this is the highest exponential. Fourier transform gives you the complex exponentials in a signal. A complex exponential is a frequency. So once you do this, plot this, you can figure out the maximum frequency exponential, which is basically a high frequency, a cosine, maybe a sine, in the frequency domain. It is, if you see this spectrum on both sides, it means it is just a cosine, because remember, two exponentials here, exponential here and exponential here means a cosine. So usually for real signal it is a cosine. So means there will be a high frequency cosine. Okay, now here is a question. If you have a cosine, how many samples are required to capture this cosine? आपको एक cycle, if you want to capture a cycle in this cosine, what do you think? How many samples are required to capture a cosine? 4, 2, more than 2, 3. 2 will be fine if you sample it here. So 2 is fine. Okay, 2 is fine if they are not really happening on exactly on 0. So 2 are fine. 2 samples are okay, or maybe a little bit more than 2. More than 2 means 2.1 or 2.00001. That after a while you get 3, but 2 are fine. Why? Because a D to A converter is a smoother. Once you put this signal, this is very interesting. If you put this signal, and actually we have done this, if you do put this signal to a D to A converter, it will generate a sinusoid. So the magic in a D to A converter is that it can interpolate and generate a frequency. So you do put this, it will exactly generate this, because it has a sample and hold, and then going through a smoother or a low pass filter will generate a cosine for you. Okay?
So what if we have we want to represent a triangular wave?
If you want to represent a triangular wave, the triangular wave has several frequency contents. Look, if you have a triangular wave, the question is, the trick is simple. The triangular wave, find the Fourier transform. If you find out the Fourier transform, you'll find out it has so many frequency contents. So you will not able to simply do it by taking 2 samples of this frequency. You will end up taking a lot more samples to actually generate a triangle, because triangle just keeps running in frequency domain. Okay, so not for triangle, it is only for sine and cosine. So the point is that the highest frequency content, more than 2 will not hurt. In a cosine, if you have 3, no problem. If you have 100, no problem. Okay, so means more than 2 will not hurt. A 2 will create a cosine for you for sure. Okay, so it means if I have all these frequencies in my signal, okay, it's the Fourier transform will tell me, okay, I have all these frequencies. I find out the highest frequency. I say, okay, this is the highest frequency, and frequency means a sinusoid. I say, I really want to capture this. I don't want to let it go. Let's say it is at 4 megahertz. If the highest frequency is at 4 megahertz, how many samples do I need? 4 megahertz in every cycle I need 2. If it is 1 hertz, I need 2 hertz. If it is 8 megahertz. So 8 megahertz will make sure that at least I have 2 cycles in 2 samples in a cycle. We'll make sure that. I will have 2 samples in one cycle of the highest frequency content in the signal. What about the frequency content which is at 2 megahertz? How many samples will I have in that? 4. Will it hurt? Obviously not. Okay, let it be. The signal is not disintegrated into cosine. Okay, signal is not disintegrated in cosines. Signal is just a signal which is a combination of all these cosines with the highest frequency content, maybe just riding here in a signal, highest frequency. You know, a signal may be like this. So there is a low frequency and there is a high frequency. Okay, to capture the high frequency, I need to sample it fast enough that at least I get 2 samples in every of this. Otherwise, I will not able to catch these details. These details will go away. I'm not sampling fast enough. Okay, then you will not able to capture the high frequency details in a signal. This is the time domain signal. It has low frequencies components and high and medium and very high frequency content. My interest is to capture those high frequency content as well. Now let's see a case where though the signal has a very high frequency content, but I don't have a fast enough A to D converter that can actually sample this high frequency. So I have an A to D converter which samples and tries its best, goes here. This is the best it can do. Okay? So no 2 samples in a cycle. It takes sample here, then comes back here, comes back here, comes back here. Now remember, once you sample, sampling means you sample then you throw away. You don't know. Once you store, you are only storing these samples. So this information is no more there. Once an analog signal goes through an A to D converter, you have only the samples. The rest of information has gone. You have no way of knowing that the information, the high frequency information was there. Okay. Now once you pass this to a D to A converter, the best it could do is that it'll try to find us this. What is this? It is a high frequency? No, it is a low frequency. So there are 2 problems with this. One problem is you will lose for sure. You will lose for sure the high frequency part of your signal. So you're going to lose that. This is one problem. There is another problem, and what is that? Aliasing. Like what does aliasing? Which 2 frequencies? You see, this frequency may already be there in the signal. Okay? This frequency, what you have generated, which is not the true content of your signal. This is because you could not sample fast enough. It has generated another frequency, which may already be there in your signal. It will go and corrupt that. It will be added. The effect will be as if this frequency is being added, this particular frequency is being added into the original frequency, because we saw a spectrum. So you could not sample 4 megahertz, for example. So you tried using a lower frequency A to D converter. It will map, let's say, 4 megahertz to 2 megahertz. So the 2 megahertz frequency content will change. It changes depending upon how it gets added, phase, out of phase. It may be completely removed. It may be added depending upon what happens. But the problem is, if you are not cautious about this fact, you need to know that just sampling a signal which has higher frequency content at an inappropriate rate will not only affect you to lose this, okay, it will also in fact come back and affect up a frequency. But if you are not only not sampling this appropriately, you are sampling the entire half of this band inappropriately. So for example, you say for sample 4 megahertz I must sample it at what rate? 8 megahertz, but you only sample at 4 megahertz. So at 4 megahertz mean what frequencies are you precisely capturing? 2 megahertz. What will happen to frequencies 2 to 4 megahertz? They will come and corrupt the 2 megahertz frequency. You will get nothing. Okay? We'll see how, but literally, if you don't sample it appropriately, you may just get garbage, nothing else. Because every frequency will come and corrupt a frequency for sure. Every frequency, higher frequency, will come and corrupt a low frequency which may already be there in the signal, fine. Which may not be there in the signal, will start appearing here. Okay, the frequencies which were not there will start appearing on this side. And this will go away. Once you again take the spectrum, this is, let's say, the spectrum of a continuous time signal, and then you discretize, inappropriately discretize, see the spectrum. You may find spectrum just doing this everywhere, and not that what you are seeing on the analog spectrum. This is the digital spectrum, may be totally different than the analog spectrum, and this is the reason that if you don't sample fast enough, you are generating a frequency. So though you are losing the high frequency, but you are generating a frequency which will come back and corrupt the original frequency in the signal. I think this is I don't intend to take class on Friday. I'll take it on next Friday क्योंकि आपका sessional है. So the sessional is till Z transform. So today's lecture Wednesday है ना? नहीं, मैं कह रहा हूँ I know Friday को नहीं है, but I'm not taking class on this Friday. आप इस Friday को class नहीं है, अगले Friday को extra class जो मैंने रखी है, I'll be on the next Friday. So you go relax and sessional क्या है? Cheating करनी? जी? मुझे नहीं समझा. एक Wednesday sessional is on Wednesday. हम काफी लेट हो गए हैं sessional. Cheat sheet allowed है.